In this lesson, we're going to be looking at properties of rational exponents. So the rules that we use are the same that we would use for any exponents, which means the base needs to be the same when we apply the rule. So the first rule is when we multiply exponents with alike bases, we add the exponent. So we can do the same thing with fractions in the exponent. So the base is 7, and then I would add 2/3 and 1/3 to give me 3/3, and then we simplify and it would be 7 to the first. So again, as long as the base is the same, you can add the exponents. You may even have to get a common denominator. The denominator doesn't have to be the same, but we can add those exponents together to get a simplified single expression when we work. We also have the power to a power rule. And for the power to a power rule, everything inside the exponents has the multiplication applied to it. It's not the exponents. Everything inside the parentheses gets raised to that power. And we multiply the exponents. So I can take, it doesn't matter what the base is, I would take the two exponents and multiply them together. So 2 over 1 times 3 over 2. This one's nice because those are going to cancel. And I'm going to be left with x to the third. Okay, so again, everything in the parentheses gets raised to the power, and then we would multiply. So here I would have x to the third to the 1/3. Well, 1/3 of 3 is just 1. So those actually cancel out and we're left with just xy. For quotient, we divide exponents with like bases using subtraction. So we would subtract the exponents. So in the example here, we have a 2, and then I would subtract the exponents of 4/5 and 1/5. That up in the exponent. So 4/5 take away 1/5 is going to be 2 to the 3 over 5. And then you could even take that further and write that as a radical. So we would be a 5th root and 2 to the 3rd power. So that's as simplified as that one's going to be. If we're dividing and have an exponent on the outside, we use the quotient property, meaning that the top and bottom both have to be raised to that power. So for this example, we would multiply x to the 5th, and then it would be multiplied by 2/5. And then the denominator is y to the 10th, and that also gets multiplied by 2/5. So in the numerator, the 5's are going to cancel. I'm going to be left with x squared. In the denominator, we would do 10 times 2 is 20, and 20 divided by 2, or excuse me, by 5 is 4. So we could even say x to the 4th. So this one will simplify more because I can go ahead, or no, it can't because I wrote the wrong variable. That's a y. If it was an x, we could simplify more because it's a y, and I didn't catch that when I did that before. That would be our most simplified expression. So when you're working with the rational expressions, you just want to think about what would I do if these were whole numbers, and you can apply all of those the same way that you did with the others. So when we started talking about radicals in the last unit, we said, well, we're going to combine them. They need to be the same index, meaning the number over here in the front of the radical. But if I change them to rational exponents and the base is the same, then I can operate with the fractions. So 3, the square root of 3, I can rewrite that as 3 to the 1/2. And then the second one will be 3 to the 1/4. So now we're multiplying exponents with like bases, which means I add the exponents. But in order to add those exponents, they would have to, because they're fractions, they would have to have a common denominator. So I can change that 1/2 to be 2 over 4 so that I can add those fractions. So 2 plus 1 would be 3 to the 3/4. And again, we could rewrite that in radical form using 4 as the index, and then this would be 3 to the 3rd, which would be 27. We can do the same thing with division. So if I rewrite that radical using a rational exponent, so x to the 1/3, the denominator would be the 2/3. So because it's division, we subtract when we have a like base. We already have a common denominator, so I don't have anything I need to do there. I can go ahead and just subtract. So that would be the negative 1/3. And if I have a negative exponent, we can rewrite that in the denominator. 1 times the cube root of x. If we didn't, because we don't typically want a radical in the denominator, we can also rationalize with these. It takes a little bit more than just the square root, because I need to make this have a group of 3, and I only have one x, which means I need to have 2 more under the square root, because that would then simplify. And then I have to multiply the same thing on the top. So anything times 1 is itself. And again, if I, in the denominator, these are both the cube root, and then I would say x and x squared, that would give me x to the 3rd, so the cube root of x to the 3rd is just going to be x. So if you're ever in a position where you can't write that as a radical, you can, you just got to think about how many more do I need to create a group together, so that I would not have to write that with a radical and then multiply top and bottom. So we have calculators. So now, trying to think about, these are still rational exponents. I just wrote them as a decimal. So, you can always just go into the calculator and simplify that. Some people like to, do things without a calculator. If you take the SAT, you have some things you're going to have to be able to do with a calculator. So we can kind of think about this like it's a power to a power. So I can rewrite 9 as 3 squared. And then negative 3.5, so that would be negative 3.5. If I'd make that into an improper fraction, it's negative 7/2. And if I use the power to a power rule, then I'm going to multiply those exponents together. And so what happens is when I multiply 2/1 times 7/2, that cancels. And I would get 3 to the negative 7, which would be 1/3 to the 7. So 3 to the 7 is a little bit more easy to work with and think about without a calculator than the negative 3.5. And then we could also convert it to a radical. So this would be 9 to the negative 7/2, which I would rewrite, make it positive. So again, all of those rules still apply. So it'd be 1 over the square root of 9 to the 7th power. I don't even know what 9 to the 7th power is. That's a really big number. And then we would have to take the square root of that. It's like 4,782,969. And the square root of that is 2187. So let's see here. 1/3 to the 7th is 1/287. 2187, sorry. So we got the same answer. Again, we have access to calculators. I don't necessarily need to convert that to something that is not a decimal, but it is nice to see some of those properties applied to those exponents.